Welcome to this explainer. Today, we're basically acting like magicians, revealing the secrets behind the ultimate magic trick. Look, we hear about AI every single day, and you probably use these tools constantly to write emails, brainstorm ideas, or debug code. But very rarely do we stop and look under the hood to see how large language models actually work. What is genuinely happening behind the screen when you hit enter? Well, we're going to open up the black box and find out. You might think an AI is this massive, sentient brain living somewhere in a science fiction cloud, but the reality is surprisingly grounded. An LLM is essentially just two self-contained files. If you take an open-source model like Meta's Llama 2, you really just need a parameter file holding the network's weights and a run file, which, get this, can be a simple 500-line C program. You can literally run this right on an unplugged MacBook. It is fully 100% self-contained.
So here is our roadmap into that black box. We'll be covering the two-file illusion, predicting the next word, the lossy filing system, hallucinations and inscrutable artifacts, and finally, thinking fast and slow.
All right, diving right in. Section 1, the two-file illusion, compressing the internet.
To actually get those two magical self-contained files onto your laptop, we have to start with something impossibly huge, the entire internet. Companies begin with this massive, incredibly messy crawl of the web, downloading articles, forums, wikis, you name it. We are talking about roughly 10 terabytes of raw text. To put that into perspective, that is billions and billions of pages of human output. Every Wikipedia article, every heated Reddit debate, endless lines of computer code, all scraped together just to form the foundation.
Then, they feed all of that raw, messy text into a highly specialized, incredibly heavy computational cluster. We're talking around 6,000 high-end GPUs running nonstop for about 12 days straight. This isn't just a powerful computer you can buy at a local electronics store. No, this is a massive, warehouse-scale supercomputer churning through data at a scale previously unimaginable in human history.
And as you might guess, this intense training process, not cheap. It costs roughly $2 million just to run the calculations for a single 70 billion parameter model. And for the larger, cutting-edge, state-of-the-art models you likely interact with daily, you can go ahead and multiply that financial cost and physical scale by a factor of 10 or more. The barrier to entry here is just absolutely enormous.
But here's the incredible part, the absolute magic trick of this whole process. All that intense computation, the millions of dollars, the terabytes of messy internet text, it all culminates in a surprisingly small 140 gigabyte parameter file. That file holds the entire network's mathematical weights. You can really think of this massive multi-million-dollar training phase simply as the ultimate data compression algorithm.
Let's move to Section 2, predicting the next word, the core mechanic.
So what do those 140 gigabytes actually do when you type a prompt into them? Well, the underlying transformer architecture isn't really thinking the way you or I do. It's performing a massive mathematical calculation. It simply takes your input sequence of words, fires its dispersed digital neurons across billions of parameters, and spits out a statistical probability for what the very next word should be. You give it words, it predicts the next one. It is basically the world's most complex autocorrect.
Which brings us to Section 3, the lossy filing system, storing world knowledge.
Here is the truly fascinating part about that core mechanic. Just by trying to accurately predict the next word in, say, a Wikipedia article about a historical figure, the model is forced to internalize facts about the world. But remember, those 140 gigabytes act as a lossy compression, an imperfect zip file of the internet. It doesn't save a perfect verbatim text document of the web. It captures the gestalt, or the approximate essence of all that original information.
Think of it like a massive library containing all of human knowledge. But instead of the books sitting neatly and predictably on categorized shelves, imagine all the books have been taken down, completely shredded, mathematically analyzed, and then rebuilt as a complex web of numerical weights. It's an incredibly dense, unified filing system. The facts are in there, scattered across the entire network, but retrieving them perfectly every single time is tricky, because at its core, it is an imperfect database.
This imperfect retrieval leads us to Section 4, hallucinations and inscrutable artifacts, the limits of memory.
Because this filing system is lossy, the model effectively dreams internet documents when you let it run loose. For example, if you ask it to generate an Amazon product page, it perfectly mimics the format, the titles, the authors, the specific layout.
but it will confidently hallucinate completely fake details, like a non-existent ISBN number. The exact real-world ISBN was lost in the compression process, so the model just mathematically guesses what number should go there to make it look right.
And this leads to what researchers call the reversal curse. And honestly, it shows just how alien this technology really is. If you ask the model, who is Tom Cruise's mother, it easily retrieves the answer, Mary Lee Pfeiffer. But if you reverse the question and ask, who is Mary Lee Pfeiffer's son, the model suddenly has absolutely no idea. The knowledge retrieval works strictly in one direction. It's a completely bizarre, non-human way of storing and accessing information.
So how do we push past this? Let's look at Section 5, Thinking Fast and Slow, the future of AI reasoning. To fix things like the reversal curse and those weird hallucinations, we can draw from Daniel Kahneman's famous psychological framework. Current LLMs are basically stuck in System 1. Much like your reflex to immediately hit the brakes in traffic, they are instinctive, fast, and automatic. They just predictably spit out words, chunk, chunk, chunk. But complex problem solving, that requires System 2, a slower, conscious, rational process where you build a mental tree of possibilities, evaluate them, and choose the best logical path.
Right now, when you hit enter, language models lay down track in mere milliseconds. They answer instinctively, predicting the very next word at lightning speed. But the future goal of AI development is purposefully trying to slow them down. Researchers want an AI that can actually take minutes to reflect, to internally debate itself, and to build that conscious tree of possibilities before it even outputs a single word to you. The absolutely crucial point here is converting computing time into accuracy. Imagine a world where, instead of demanding instant answers, you hand the model a highly complex problem and say, take 30 minutes, map out every possibility, debate yourself, and give me the absolute best mathematically sound answer. That capability of deep, slow reasoning doesn't quite exist yet, but it's exactly what the entire industry is intensely racing toward right now.
To truly achieve the System 2 thinking, models need to move beyond just imitating the human labelers who initially trained them. We saw this evolution with AlphaGo, the AI that mastered the complex board game Go. It surpassed human ability not by copying us, but via self-improvement, playing millions of simulated games against itself, because the win/loss reward was obvious. The grand open challenge in AI right now is finding that equivalent, mathematical reward function to let LLMs self-improve in the open-ended, extremely messy world of human language. This is why we have to fundamentally shift our perspective on what these tools actually are. We must stop seeing these models as mere chatbots designed to answer trivia or write polite emails. Actually, scratch that. They are the kernel process, the central foundational brain of an entirely new tool-using operating system, an OS that can already browse, code, and draw, and very soon will be able to robustly reason. Which leaves us with a massive, industry-defining question to ponder as we watch this space evolve so rapidly. What actually happens when we successfully give this imperfect, lossy filing system the time, the architecture, and the structure to truly think before it speaks?
The leap from simple human imitation to autonomous self-improvement is the next holy grail of computing. Understanding these underlying mechanics, the lossy compression, the transformer architecture, the aggressive pursuit of System 2 thinking, that is your first real step into that fascinating future. So next time you type a prompt, ask yourself, is the machine just predicting the next word, or is it finally starting to think? Thanks for joining me on this explainer, and I'll catch you next time.